In this video we have another application of Extrema. In this case it's a relative minimum. We have two posts, one 20 feet high, the other 28 feet high. They are 30 feet apart. They are to be anchored by wires attached to a single stake running from the ground level to the top of the post. Where should the stake be placed to use the least wire? So we're trying to minimize the length of the wire. You want to give this a try here, you can, or you can start when I give you a diagram of this. So here's a diagram of what we have. One post on the left, 20 feet high, the other one on the right, 28, and we have the stake somewhere in between, and we have the length of one wire from the stake to the top of the post that's 20 feet high is Y, and the one going to the other one is Z. So we're going to pause the video here and try it. Go ahead, and then I'll be back. So first we need to define the function for the length of the wire. So I want W, and eventually I'm going to want this in terms of function of X. So this will be whatever the length of Y is plus whatever the length of Z is to start off with. And we have two triangles here, two right triangles, here and here. So now we know that Y then is the hypotenuse, so it's going to equal to the sum of the squares of the other two sides. So Y squared will equal to 20 squared plus X squared. And then solve for Y, we take the square root. So that'll be the square root then of X squared plus 20 squared. It's 400. I look at the other triangle, Z squared. Its hypotenuse will equal to the sum of the squares of the other two sides. So Z squared will equal to 30 minus X. Again, remember they're 30 feet apart. So if I let this length here be X, then the other one has to be 30 minus X. So Z squared will be 30 minus X quantity squared plus 28 squared, and then we take the square root of that. So you do the algebra there. This comes out to a square root, and this will be X squared minus 60 X plus 900. That's this squared, and then you square the 28 feet and add the result of that quantity, and this will come out to a plus 1684. And based on the diagram, we know that X then, whatever X turns out to be, has to be some number between 0 and 30. So that's going to be the limits on this. X greater than or equal to 0, less than or equal to 30. And that's your function that gives the length of the wire. So then all we got to do now is compute the derivative of this and find the critical numbers. So this is a radical here. It's X squared plus 400 to the 1/2, so the 1/2 will come out in front. And then we subtract 1 from the exponent, so that'll give us X squared plus 400 to the negative 1/2, take it to the denominator, and then this will be, using the chain rule, will be 2X, but we have a 1/2 in front, so this is just be X over the square root of X squared plus 400. Again, this was to the 1/2, so we bring the 1/2 in front, and then the derivative of this inside is 2X, so the 2 cancels with the 1/2 in front, and then we subtract 1 from the exponent. It makes it to the negative 1/2, take it to the denominator. And the same sort of thing here in the next one. We're going to have the 1/2 out in front. Then we eventually have to take the square root, the derivative of the Vatican. That'll give us 2X minus 60. Got the half over here, so that'll give us X minus 30. And then we subtract 1 from the 1/2, makes it negative, so we take it to the denominator. We get X squared minus 60X. Plus 1684. So that's your derivative. So now we just gotta figure out what are the critical numbers. So we want to set this equal to 0 now. Set that equal to 0 and solve for X. So what I'm going to do then is I'm going to bring this over to the other side, and then I'm going to cross multiply. Here's what we have then. Be X. This goes over, and then I'm cross multiply. So this will be X, and it's the square root of X squared minus 60X plus 1684. That'll equal to, okay, this came over, so all I have to do here is just change the sign of the numerator because it goes to the other side. Okay, just so it's clear here, what I did is I took this term over to the other side and it changed the sign here. So I put it, instead of X minus 30, it becomes 30 minus X. And then I cross multiplied, so this expression here multiplies the other side, and then this multiplies the X over here. And now it's just a matter of, it's convenient here because you got a product here. square both sides. So obviously on this one here, you're going to have an x squared. And then when you square the radical, it cancels the radical and it leaves you the radicand. So all you got to do is multiply x squared times x squared minus 60x plus 1684. And over here on this side, obviously when you square the radical, it leaves you with x squared plus 400 in parentheses. Then you square this part here, 30 minus x. That gives you 900 minus 60x plus x squared. You multiply term by term. And it's a little messy with the algebra, but again, you do the squaring on this side, do the squaring on this side, and then bring all your terms over to the other side. So let's give us some room here. Now, if you do those calculations, bring everything to the other side, you get some large numbers, but it becomes a quadratic equation. Simplifying the right side, simplifying the left side, and then bringing the terms on the right side to the left side, that gives you 384 x squared plus 24,000 x minus 360,000 equals 0. And then you're going to play around with your factors, but every one of these numbers, the 384, the 24,000, the 360,000, is divisible by 192. So divide through by 192. 2x squared plus 125x minus 1875. And this is equal to 0. And that's as far as we can reduce this, but then we try to factor again. Factors of the 2 here are just 2 and 1. Then you're going to play around with the factors of 1875. That's just algebra. This factors into x plus 75 and 2x minus 25. Now there's a lot of calculations, a lot of algebra, but it's not a difficult problem other than doing the calculations there. So you set the factors equal to 0, and one possible solution we can get here for x is negative 75. Obviously here we have to reject this answer. Can't have a negative value in these types of situations. And then this one here, 2x minus 25 is equal to 0. Solve for x here. X is equal to 25 over 2, or 12.5. And remember, we're looking for numbers between 0 and 30. Now, in some of these problems, you could try the endpoints depending on what's given. Because here's a situation. I mean, you could have a graph. Let's say the value or the domain of the x that you're using goes something like that. If you're looking for a minimum, you always want to try the endpoints. In this case, you can. The way I do it here, the minimum is going to be there. So it's going to be at the point where a value where the derivative is 0. But you might have something like this. It might look something like this. If you're looking for a minimum, well, here's a relative maximum, minimum here. Here's a relative maximum here. But if you're looking for a minimum, smallest value you can have in that interval, it's going to be at x equal b. So always be aware that sometimes for these types of problems, whether you're looking for a maximum or a minimum, it could be, usually it's going to be at one of the critical numbers, but it's possible it could be at one of the endpoints. So you always have to keep that in mind. In this case, we have 0 and 30. But by the diagram, that's not feasible. That's not going to be feasible here, using 0 for x or 30 because of what we have here. So the endpoints are not feasible in this particular case. So the only option we have is 12.5. We simply have to test it now. We're looking for a relative minimum in this case, so we plug in that 12.5, pick a number larger than that, say 13. 2 times 13, 26 minus 25, that's positive. And of course 12.5 and 75 is positive, so in here it's a positive. If we pick a number less than 12.5, say 10, this will be positive, and that second factor will be negative, so it's negative here. If I look at the graph, negative means the graph, negative derivative means the graph is decreasing, so it's coming down here, and then it reaches a low point at 12.5, and then it's positive, then it goes up. So the answer in this particular case, the relative minimum is going to be at 12.5. In this case, the units are feet. So to answer the problem then, where should the stake be placed to use the minimum amount of wire? And it should be placed 12.5 feet from the 20-foot post. Thanks for watching. We'll see you next time.